Right, so now we know what we need to plot. What we've got to do is get our raw data into a point where we can plot that. So again, go back. What have I got raw data on? I've got raw data on V and I. I need R. So what am I going to do? Let's make ourselves a little to-do list at the side here. What am I going to need to do? I'm going to need to calculate resistance R. In order to do that, I'm going to need to get my mean values. So if you've just done means of V, that's okay. Ideally, you should have recorded I and V. But if you've just done mean values of V, then at this stage you'll get away with that. That's okay. So I need to calculate my mean values of V so that I can calculate R. I need to calculate the area. So I need a mean value of diameter, and then I need to calculate my area. And I need to make sure that that's in meters squared. Alright, everything else is already in volts, amps. But I need to make sure my area is in meters squared. And then what do I need to do? I need to plot a graph with R against L. Then what do I need to do? I need to get the gradient. Running out of space. Plan ahead. There we go. And then from that I need to calculate rho, which is area multiplied by gradient. So m is the gradient. Calculate rho as area times the gradient. So that is my little to-do list. And that is my processing to-do list. So that is going to give me my answer. Okay, so let's take a little closer look at some of the aspects of that. But ultimately, you've just got to do the number crunching now. Now, there's one more little bit of that I'd need to add. It's not part of the processing, but you probably want to bear this in mind because you end up with a lot of work if you leave it all to the end. You need exemplar calculations. Remember in the example, and all the videos that you've watched that take you through the example, exemplar calculation. So for every type of calculation, so an example of a mean calculation of V, just one, an example of a calculation of R, an example of a calculation of mean D, of area. You need to show the calculation of the gradient and how you then use the gradient and the area to get resistivity. So you need one of each of those calculations, and obviously the ones at the end, there's only one calculation anyway. So that's the only other little bit to make sure you add to that. So let's pop my little to-do list down here. Oh, just one of them will do. Okay, so I'm not going to waste your time and insult your intelligence by reminding you how to do mean calculations. But there are one or two little things. So number one, mean calculations. This was mean V. Alright, obviously you add the number of V's up and you divide by how many you've got. That's easy. Notation. Be really careful with this. If you've got repeat readings of V1, V2 and V3, but if you've used, for example, V1 and V2 to distinguish the two different voltages or potential differences that you've collected, because remember there's two different ones, that's now going to be really confusing. So again, you've got to think about what you're doing. Don't just scribble it down really quickly. Each of these in your raw data has got a unit, and each of these also has a plus or minus error. I think most of them have been about sort of 0.005 of a volt. So make sure you've got all that. Now, when you come to work out your mean value for potential difference, it needs one of those things. Well, two technically. It needs its own symbol, so it needs V. You can do V bar if you want, statistical symbol for average of a quantity, absolutely fine. You can use the word mean. Don't use the word average, because there are three types of average, and it's a mean, so call it what it is, it's a mean. Yes. Or use V bar, acceptable as notation for the mean. It also needs to have a unit. Okay, and it's in volts again. It does not need an error in the heading. No. Because what's going to happen is each of these is going to have its own error value, and we're going to worry about error values separately. what else do we need to think about? In the body of your table with your repeat readings, I've done this a little bit tiny just to fit it in, but you might have, for example, 2 decimal places, let's say. Or 3 decimal places. You might have included the extra bit as an error. And then you could give these as 1.220 or 1.340. Let's say, for the sake of it, you've done these as 2 decimal places. Then your mean also needs to be 2 decimal places. Or it needs to match. So it needs to match your raw data. And the same is true for anything where you do means. So the same is true for your mean value of D as well. You need to make sure that they're recorded, that you've worked out a mean value of D, that it's got its unit. I would do it in meters if I were you. So your raw data for D might be millimeters, but I convert it to meters when you do the mean. Or do a mean in millimeters and then another column with a mean in meters. Nothing wrong with that. But I would convert it to meters at that point. And then it's ready for when you do the calculation of area. And you need to put in an exemplar mean calculation. So you can give a bit of an explanation. It's almost like a formal one. It doesn't have to go on and on and on, but you just need to go, equation, put some numbers in, show an answer, give a little caption to say, this is the calculation of the mean potential difference. Bum, 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 bum. That's all it needs to be, but it needs to be there. We need to see that. We need to see the same thing for the diameter. Okay. There is no error, so we'll worry about that a little bit. Okay. Likewise, then, for your calculation of R. So, number 2. Calculation of R. So remember that R equals voltage divided by current. You shouldn't really collected anything in, I don't think, anything that was other units. But it does need to be volts and amps. So if you have happened to done it in millivolts or milliamps, then you need to make sure that they're in amps or volts before you work out R. And R has the unit of ohms, which is a little omega symbol. Now, for this, you think about significant figures. So, where this appears in the table, you might want to put this in a separate part of the table. Bear in mind, it's going to need its own error calculations as well, just like V is. So you might want to kind of just give it its own table somewhere. So for that, you also then need to have, like a run value or something where you've just got 1, 2, 3, 4. And then you can have the equivalent resistances down the side. So then you look at the information you've got. So for example, let's say that you used, for a value of R, a current of 0.10. That's 2 decimal places. It's also 2 significant figures. Yes, the 0 is significant, the second one is, the first one isn't. So your 2 decimal places are these 2, your 2 significant figures are these 2. If it was 0.11, it would be exactly the same. If it was 1.11, then it would be 3 significant figures. Let's say then that we also got a voltage of 1.25. So current is in amps, and that one should be in volts. This is 2 dPs, but it is 3 significant figures. So in this instance, and again, you've got to look at your numbers and your data and see how many significant figures you've actually got, and you've got to apply this idea to yours, but you've still got to look at your own data. Don't just blindly follow what I'm doing. I'm doing this with these numbers. Yours may be different. So R would be voltage divided by current. So R would be 1.25 divided by 0.10, and therefore R would be 12.5 ohms. And if you're doing your exemplar calculations as well, don't forget, include some units and a bit of an explanation in there as well. You don't have the benefit of a voiceover. Now, I've got 2 significant figures and 3 significant figures. What's the weakest link? The weakest link is the lowest number of sig figs. So I can only really give my resistance to 2 significant figures if it's in the final answer. But if I'm sort of plotting it on a graph, then I can give a little bit more. Okay, so it would be acceptable at this point to perhaps give an extra little bit of a significant figure, but generally this is covered by the fact that due to putting your errors in your current, you've probably gone to an extra decimal place with each of these. And if you just follow that through to your resistance, then you'll be absolutely fine. But strictly speaking, this can only be written to 2 significant figures. So, in actual fact, we can only give a resistance value of 13 ohms. Now, where this really matters is right at the end. So for me, as this is intermediate workings, I would give this to slightly higher significant figures. But the final answer, I would look at all of the numbers that I've used to get to that point, get to that value for resistivity. And if the least number of significant figures in all of those numbers is 2, then I can only give my final resistivity to 2 significant figures. Okay? But you want to bear the sig figs in mind as you go. What I certainly don't want to see is lots of decimal places. So if this was 0.33333, I don't want to see 0.333 written millions of times. Alright, I want you to look at it and go, okay, I can give this to 2 significant figures, so I'm going to give it to 13 amps. Because generally that's the level of precision you're limited to. So 2 significant figures would be absolutely fine, and that's what we'd expect. Okay, one other little side note on that is ultimately you're going to plot R, so there's no point giving it to more significant figures than you can plot. Or let's say there's no point worrying about it. But if you had to give this to 4 significant figures, you'd write 4 significant figures down. You might be able to plot it to that level of precision, but that's not for you to worry about. So you just follow it through from your raw data. Okay, so what's next? We've got our mean value of V, mean value of D, we've calculated a value of R. We now need to calculate the areas. So again, same thing. Only thing I'm going to say about this is, remember, you can use area equals 4, you can use pi d squared over 4. You don't need to, that'll probably work better like that, won't it? There we go. You don't need to halve the d to get an r and then use pi r squared. Just use pi d squared over 4. But that needs to be in meters. So that will come out in meters squared. So check it's in the right units. Also think about significant figures here as well. Okay, so if your diameters are 2 significant figures, you can only really give your areas really to 2 significant figures. So that's all of the data. Now, what you've got there is resistances. So that's a y-axis taken care of. When we calculate the gradient, we've got now a value for A. Obviously, our value for A is based on the mean value for D. Likewise, our resistances that we calculate up here use our mean values for V and I. You don't want to be calculating 5 different resistances, all right, or 3 different resistances. You just, one mean value for V gives you effectively like a mean value for R. Now, the only other thing we need to just make sure of is, for part 4, we'll talk about the graph more in just a second or two, but the final little thing is just put your lengths into meters. So if you've got all your lengths recorded in centimeters, you know what, that's fine, that's not a problem. But put them in meters and keep the same level of precision. So if you had a length of 0.1, if you had a length of, let's say 10 centimeters, that should be recorded as 10.0 centimeters because you're measuring to the nearest millimeter. So in your raw data, make sure that you reflected that level of precision. You didn't measure it to the nearest centimeter, it was to the nearest meter, the nearest millimeter. So it should be 0.0. If your plus or minus takes you to an extra decimal place, it might even be 0.00. Okay, so you then need to perhaps have another column where you write down the values of L in meters, and you divide these by 100. So you need to keep the same level of precision. So that, for example, 10.00 would become 0.1000. What have I got? 4 sig figs. What have I got? 4 sig figs. don't lose precision at this point. Even if they're zeros, you still want the sig figs. And then every one of those should be 4 sig figs going down. If your L values are recorded to 3 sig figs, your L should be 3 sig figs going down. I don't think this should have happened to anybody, but if the number of significant figures were to change halfway down a table, so I don't know, let's say you did your first length was 5 centimetres, so you might have 5.0, well that would become 0.050. That's 2 sig figs, that's actually 2 sig figs as well. The next one might be 10.0, and that becomes 0.100. That's 3 sig figs, that's 3 sig figs as well. So it can change going down a table if your raw data changed. It doesn't have to be consistent in a column. Each value depends on the value made to make it. And the same goes for your calculations of resistances as well. It might change significant figures from one to the next if the sig figs of your voltage or your current changed as you were going down.